Hello. And we're going to learn about Lewis structures. It's your pre-lecture. And hopefully I'm recording with my voice this time. So, Lewis structures. They're also known as electron dot structures. Gilbert Lewis. It's only about 50 to 70 years ago, not that long ago, came up with this way to represent molecules. It's really amazing. Linus Pauling, who's from Oregon, also came up with a method, but we follow Lewis structures method. And it's a way of showing how molecules come together. And it's really amazing because the whole field of molecular biology and stuff, if you think about it, they didn't have that. These guys are the ones who allowed this groundbreaking because they asked these questions. So it's all about covalent bonds. And covalent bonds are sharing electrons. And we're going to represent them that 2 electrons is going to be a line. 2 electrons that we share are going to be a line. All right, so the example we're going to do, we're going to walk through the steps. Your lab has all the steps beautifully written out. So realize that, but it's really nice to write down notes also. And then when you do the lab, this will all come together. All right, our first example is NF3. So we're going to walk through the steps with the NF3. And the first step is the key. All these steps are really important. But that first step, counting valence electrons. That's where I realized my dilemma. Because it used to be you all had my periodic table. And my periodic table used A group numbers. And you probably heard me talking about this. Well, the very last page of these notes is the electronegativity table. And we'll get to that in class. But what I wanted to talk about today, if you notice, when Linus Pauling came up with this table, brilliant, 2 Nobel Prizes, he used A numbers. The A group numbers are the older ways. And the A group numbers make it easier to count our valence electrons. We're only worrying about S's and P's. Now, since we're doing covalent bonds, we're working with non-metals. And so non-metals, right, our periodic table, they're over in this upper corner. So they're all in the P group. So the S's and P's matter. So you're going to count your valence electrons, which is their A group number. So going backwards from the noble gases would be 8 valence, then the halogens would be 7, and then 6 for oxygen's family. Nitrogen's family will be 5. Carbon's family will be 4. Right, that's what we did. Nitrogen is 5 valence electrons. And then there's 3 fluorines, and each has 7 electrons, valence electrons. Only the valence electrons are going to react. And we add this all up, and we get 26. 26 is the number we need to work with. So that's our first step. The second step is we figure out the center. Now the key to finding the center, it's almost always the first element that's written down. The exception is acids, because we write acids with the hydrogen first. And hydrogens can never be in the center. That's your bonus question for watching this. Let me know, why can't hydrogen be in the center? All right, so center, the rule is the least electronegative. So the least greediest. That's you can get a fancy definition for electronegativity. My definition, it's the greed for electrons. The greediest, fluorine. Those of you in my Chem 104 remember NOF? Actually, my 151, we also talked about NOFs. What gnomes wear, those are the greedy hats. Nitrogen, oxygen, and fluorine, the greediest. Fluorine is the most greediest element on the periodic table. The very last page of these notes, we'll talk about it more, but Linus Pauling came up with this electronegativity chart. Really made up numbers. Somebody more recently came up with another one. It gets into more fine detail, things beyond what we need to know. But he just assigned fluorine the biggest number, 4. And oxygen the next biggest, 3.5. So they're greedy. They're never in the center. The center is going to share the most. Your center has to be the least greediest, and typically it's the first element given. So it's the furthest from fluorine. Fluorine is the greediest. That's going to be a question on your next celebration. What's the greediest one of them all? Fluorine. All right. I'm really hoping the video, the audio is working because I'm not going to do this a 4th time. All right, nitrogen's in the center. And then you make a single bond from the center to each of the others. These steps are like the shorthand steps. You can write more details from the lab, has it written out in more details. All right. You know, with this thing going, I kind of look like the evil sea monster. But I think evil sea monsters are just not understood. All right, I'm a chemistry teacher. How much more evil can I get? All right, I'm going to tell you a story. I have a good friend that I work with. I worked with for 25 years, 26 years actually. And he always would call me a witch. I feel like the lady from the Little Mermaid, right? Anyway, I only learned out like a month ago that that is a term of endearment in his culture. When somebody you cherish very much, it's like they call you a witch. And so for 25 years, I'm like, why does he always call me that? And I kind of would joke about it with him, but it's kind of fascinating to learn that. All right, so single bond. Single bond is the line is 2 electrons. Now, one of the other things that will help as you're drawing these is to do everything in north, south, east, west kind of grid. So now we're going to do an octet. The octet is for the outside. The mermaid is hard to walk in. Mermaids are not meant to walk. So for the outside atoms. And so dots are electrons. And they always exist in pairs. So 2 dots, 2 dots, 2 dots. Why do they exist in pairs? Oh, remember the spin? Clockwise, counterclockwise, we did the arrows. So they're always paired up. That makes them more stable. So my fluorine now has 8. If you do everything again in this north, south, east, west grid, it makes it really easy to see you have 8. 2, 4, 6, 8. So we do that for the other fluorine. So each of my fluorines has 8. And so our last step is the center. This has 2 parts to it. So for the center octet, extra electrons go on the center. So remember our first step? We have 26 electrons. So we count. And the wonderful thing about octets, you can count by 8s. So I have 8, 8, and 8, which is 24. If you're never very good at your times table, I won in 3rd grade. I beat Bob Henshaw. All right, you can count by 2s. You only count the line once, but it's easier to count 8, 8, 8, get 24. We have 2 more electrons. So your center, extra electrons on the center. And then you check. Do you have an octet? Is my question. Do we have an octet? If the answer is yes, you're done. And we have an octet. And we can tell that because that north, south, east, west, the line counts for the nitrogen as well as the fluorine. That's what it means to share. 2, 4, 6, 8. Everything is 8. We have 8, 8, 8 plus 2, 26 electrons. We're done. All right, there is a no choice at the end there. And that's our next one. So our next one is CO2. So pause me and try it. All right, you pause me, you're back. Did you do it? At least count your electrons. So I don't need to see the math. The answer is 16. I'm going to go through the math, because if you get this number wrong, the rest is going to be wrong. All right. You're always going to get an even number, unless it's one of those questions in the homework that says, what happened with Yoda's lightsaber? I think there's something about that with free radicals, and we'll go to that. All right, so CO2. Carbon has 4 valence electrons, and it's the valence, their group number. We're going with the A group number. If you have a table that doesn't have the A groups, back in the ion lecture, I gave you the A group numbers. All right, this little kid's mask is like poking my third eye. So hopefully I'm gonna become like enlightened here somehow. Enlightening like this. All right, oxygen's 6 valence times 2. Those A group numbers, Linus Pauling was brilliant. He won 2 Nobel Prizes. And when he won 2 Nobel Prizes, you know what the state of Oregon did? They gave him a high school diploma. So wonderful. He was a high school dropout. So see, there's hope for all of us. And then, you know what the US government did? They took away his passport. They decided he was a communist, because the second Peace Prize was for asking them to stop nuclear testing. And he did all these peace marches and stuff. You know, all right. In 151, it's going to give you guys an option, since you have to do class presentations. Do an element, you can do a subatomic particle, you also do a famous chemist, Linus Pauling. Be a great one. All right. Center is carbon. Carbon loves the center. That's why it starts with a C, like center. Single line. Dots on the outside. First 4 steps. At least go, okay, I can do that. Right? You're not going to say, I don't understand any of that. Say, okay, I can do the first 4 steps. You guys can't really make excuses, because, you know, you just rewatch the videos instead of playing video games. So we got to count before we start putting stuff on the center. I got 8 plus 8, that's 16. There's no extra. Does my center have an octet? Nope. So if you get a no over here, that's when you do a double bond. And that's why we have this example. So to make a double bond, you need to erase 2 electrons. So remember that eraser some of you have said you're going to get? This is when you really need to erase. It's not naming erased. Oh. Erase 2 electrons and move to another line. Oh, these are the people who got my bonus point tonight. All right. So we're going to erase 2 and make a line. My carbon only is 2, 4, 6. So you go, okay, I just need another line. Can you just put a line there? You cannot, for 2 reasons. 1, my oxygen is 2, 4, 6, 8, 10. That broke the octet rule. They want 8. This is all about the octet. And I now have 18 electrons. You have to always erase 2. It doesn't matter what 2 you erase, but you always erase a pair and move them. We drew something that was just wrong. We're just trying to get to a sketch so we can get to the next steps. All right. That's it. My center has 2, 4, 6, 8. It is sharing all of its electrons. So a double bond is 4 shared electrons. So oxygens each have 4 that they're sharing and 4 of their own. There is such a thing as a triple bond. What is that? A triple bond would be 3 lines, and we'd be sharing 6 electrons. All right, H2S. So way over here. Oh, I'm going to turn way off the camera now. All right, We'll do it up here. H2S. It's going to have 8. So sulfur has 6, just like oxygen, and hydrogens each have 1. So 8 is my key number. Now, there's something I didn't mention about the center. Back there in step number 2, I do mention it in the lab. There is an exception. Hydrogen's never in the center. Why? That is what you're going to email me. And the other part, which I have to explain now, so you don't have to do it in the email, but you could. Hydrogen is an exception to the octet rule. So you can give me both those things. Okay, sulfur goes in the center. Because hydrogen can never, ever be in the center. You tell me why in an email, you get a bonus point. Those bonus points add up. Much less stress. And if you dress up, it's Halloween week. Or even if it's not Halloween week, just dress up. Make your teacher smile. Might make her giggle and wiggle and jiggle and she'll be so happy. I call it hydrogen hell. Hydrogen, its octet is 2. So that's the other part. Why is its octet 2? Why don't we give it any lone pair of electrons? Once you got that, you've got it all. You're ready to graduate. We put the dots on sulfur and we're done. We got 8. My sulfur is 8. My hydrogen only has to go to 2. Right? First row, its octet is helium. I already gave you the answer. You just have to tell me that. And why can't hydrogen be in the center? Right? That's the idea. So we're going to do one more step. But what I want you to do, if you come to class and you've already at least tried sketching page 2, you'll be able to follow along, do it in pencil or something that erases. I had a gal last year who had the erasable pens. She had all different colors and it worked beautifully. She could see it. She really got this. But usually students get this. All right. We're going to do something called Vesper Geometry. So I have to find a way to erase. And since we're doing mermaids, we're going to do it with these 3 examples. Since we're on this page, just go ahead and finish most of it. So it is called the Vesper. And then geometry. Geometry. Very cool stuff. V is for valence. S is for shell. And E is for, it's all about the electrons, baby. Electron, valence shear electron pair. Because electrons always exist in pairs. And R is for repulsion. Repelling. They're repulsed by each other. Electrons have negatives. They don't want to be near each other. They're really magnetic moments. But this is what the whole theory is based off of. So I teach it. Need to erase. As electron clouds. You can also do it as balloons. If you're not afraid of balloons. All right, electron clouds. Around the center. It's all about the center atom. This is an electron cloud. This is an electron cloud. So it can be an atom with all of its pieces, or it can be what we call a lone electron pair. Again, on the center. So if we go to our sulfur, those dots and those hydrogens. Let's erase the 8. That was our electrons. We don't need those anymore. So the NF3 has 3 fluorines and a lone pair. Now, for teaching, I circle my clouds. You're going to see me do this when we do the next page. You do not have to circle your clouds. If you do, please make sure I can still see the dots. And yeah, it's like a learning tool. It helps some students. It helps me to teach and explain. All right, so we have 4 clouds, we have 2 clouds, we have 4 clouds. You can also have 3 clouds. All right, let's write it up here. So you can have 2 clouds, 3 clouds, or 4 clouds. We're only going to finish part of this chart. All right. They're electrons, clouds. They're attached to the carbon. You can't pull them off. They're covalent, right? You need a chainsaw to pull them off. They don't want to be by each other, so they're going to pull as far apart as they can get from the center. As far apart as they can get from each other, which is 180 degrees. So when you have 2 clouds, I don't know what order I put it in your chart. Geometry, 180 degrees, we call that linear. So for 2 clouds, we say linear 180 degrees. The linear is the Vesper, and the 180 is the bond angle. So the angle is a number that represents how far apart they are. The word linear is just a word that describes the angle. They always go together. All right, if we had 3, I actually made models of these. So this is, oh, there's my linear. Oh, there you go. We used to all get to play with these. And so there's my double bonds, and it comes out straight across. So what if we had 3? I didn't have an example on there. You'll have some in the lab. 3s are not as common, but they do happen. And this is 3. So if you have 3 clouds, like we have our center, and then you have 3 things around it. And notice to get to our octet, one of them had to be a double bond, right? See the double bond? This would be like if we had a pie and 3 people, and we split the pie equally, you would each get a 120 degree section of the pie. So for the bond angle for 3, we say 120 degrees. And what do we call it? Well, it's flat, like a pie, and it's a triangle. So we call it a planar triangle or a trigonal planar. It is called planar because it's flat, but it's also because if you took a plane, a 2-dimensional sheet, it would go through every nuclei in this molecule. All right, so we had 4. Oh, and this was always a trick question that I would ask. Somebody would say, oh, you'd have a 90 degree, but it's not. When you have 4, you have 109 degrees. So in the past, they used to have to learn these. Now you guys get to just write it down and just look at it and okay, which is fine. This is called a tetrahedral. Some people call it a tetrahedron. Tetrahedral is an adjective, tetrahedron is a noun. I don't care. Tetra means 4. Just did that with naming. That game Tetris, all the pieces were 4 blocks. That's what the whole deal was. So a tetrahedral is 3-dimensional. These guys want to get as far apart as they can, and in 2 dimensions, they can only get 90 degrees, but we're 3-dimensional. So this is what tetrahedral looks like. It is a pyramid with a triangle base on 4 faces. So it's not flat, it's 3-dimensional. And so in the center is carbon. This is one of the most sacred shapes there is in spirituality. It's kind of crazy, but it is what a carbon atom does. Carbons love to make 4 bonds. That's what my black represents. So tetrahedron. You're going to run into this a lot. 2, linear, 3, planar triangle, 4 is tetrahedral. All right, and then it talks about, oh, bonding atoms and non-bonding. We'll go through that in class together. But I want to mention one other thing, because it's on the last page. has to do with Linus Pauling, and I'm on the Linus Pauling kick right now. And I'm dressed like a mermaid. There's got to be a connection. There is something about polar and nonpolar. So let's look at it. This is, again, for those of you who are in my 104, you've heard this. To me, one of the most important things that we do in chemistry. One of them. This idea of a polar means a pull. Something is pulling. Nonpolar means no pull. And we'll just do it with these two. In this one, we definitely have a pull. This one is polar. It is not symmetrical. So there's going to be a pull if there's anything that makes it out of balance. So there's a pull by the fluorines. And if this had been a fluorine also, if all of the clouds were the same, it would be nonpolar. Everything would cancel out. That's what happens with the C and the O. Oxygens pull. They're greedy. They're part of the non. I don't know how to write with this. So they're pulling. But this one's pulling straight across. They're pulling equally. So this is nonpolar. There is no net pull. The negative areas of the oxygen cancel each other out. So that's polar. Something's not balanced right. So there's a pull. It's lopsided. That's what polar means. There's a lopsided, there's a pull. And nonpolar means everything balances out. There's no pull. It's all equal. All right. Where this goes with it has to do with the mermaid. In chemistry, those are terms we use because it's a bigger picture. We're looking at things that are polar like other things that are polar. My good friend, the polar bear, and her little polar cubs. Water is polar. This will mix with water. The polar bears. Nonpolar. Don't let her see it. Nonpolar and polar do not mix. They have no interest in each other. This guy's not pulling. He's calm. He's content. This guy, he wants things that are pulling. He's looking for attraction. So in biology, they use the term because biology is looking at everything from the viewpoint of us or the planet, which is water-based, 70 to 75% water. So they use the term hydrophilic. Philic is from Philadelphia, right? It's the city of brotherly love. Hydro means water. Things that are polar love water. They mix with water. Because of the pull, they have that in common. Things that are non-polar, so polar bears swim in the water in the Arctic, because it's all that's left. We're losing all the icebergs. Things that are non-polar are said to be hydrophobic. So the word phobia is fear, but they're not afraid of water. They just have nothing in common. But we use the term hydrophobic. In chemistry, we use the term nonpolar. And hydrophilic for things that are polar, because they like water. Like the mermaid. All right. No, your teacher fell over. Have a great night. Great day, whenever.